The topic that we are going to discuss is inverse function. Let us see the definition of inverse function. Suppose we have f from a to b. Suppose f is a function from a to b. Then f will have an inverse function. This is how we denote the inverse of f. We read it as f inverse, and it is a function from b to a. So f will have an inverse function if and only if f is 1 1 as well as f is 1 2. That means f will have an inverse only if f is bijective. So this is all about the definition of inverse of a function. Now let us try to understand what do we mean by an inverse of a function. So here we have taken two sets, a and b, and f is a function from a to b, and it is defined as f of x equal to x plus 8. So by the definition of f, this is the diagram of the function. Clearly here f is 1 1 as well as 1 2, because no two elements over here have same image, and every element of set b has pre-image. Now the question is, what would be the inverse of this function? First of all, this is 1 1 as well as 1 2, so this will have an inverse, but what is that inverse? So here inverse of function f will be the function from b to a, which will undo the action of f, or it will take us back from where we started. Like here, for this function f from a to b, this 1 is taken to 9, 2 is taken to 10. So what the inverse will do is, the inverse from b to a will take 9 to 1 and 10 to 2. So that would mean that the function, there would be a function g from b to a, which will associate 9 to 1 and 10 to 2. Now we observe that 9 minus 8 is 1, 10 minus 8 is 2. So we can define a function, okay, like here 9 minus 1, 9 minus 8 will be 1, 10 minus 8 will be 2. So what we do is, we define a function g from b to a, and it is defined as this, g of x equal to x minus 8. So clearly this function, okay, this function will be an inverse, because this solves the purpose, because we know that what the inverse will do. Inverse will take us back from where we started. So this function g is solving the purpose, because if I take g of 9, then it will be taken to 1, g of 10 will take you to 2. So here g defined as this is the inverse of this function f, which is defined as f of x equal to x plus 8. Inverse of f is written as this, it is read as f inverse. Okay, so gx is equal to f inverse x, and f inverse x is equal to x minus 8. We must note over here that this is not equal to this. This is simply a symbol of f inverse. Let us see another example. Here I have taken set A, set B, and function from a to b is defined as this, f of x equal to x square. This is the diagram for the function. Clearly from the diagram, it's clear that the function is 1 1 as well as 1 2. So this function will have an inverse by the definition of inverse function. Now the question is, what is that inverse? So the inverse will be from b to a. Okay, so f inverse will be from b to a, and what that inverse will do is, it will undo the action of f, or will take us back from where we started. Like here, f is taking 0 to 0, so inverse will take this 0 to here. Okay, this 0 to here, inverse will take this 1 to this one. Okay, and that inverse will take 4 to 2. So if we could find a function from b to a which would do this, okay, which would take us back from where we started, so that function will be called inverse of this f. So here we observe that if we define a function g from b to a as this, g of x equal to square root of x, then we see that a square root of 0 will be equal to 0, square root of 1 will be equal to 1, square root of 4 will be equal to 2. So we observe that g from b to a defined as this solves the purpose, because by this definition here we are able to take back these elements. Yes, so this function g from b to a is nothing but inverse of f. So that is g takes back from where we started. You can make out from the diagram given below. So here the diagram, from diagram it's clear that if we define a function g from b to a as this by this definition, then g of 0 will be root 0, that would be 0. G of 1 will be equal to 1, g of 4 will be equal to 2. So f inverse x is nothing but g of x, and f inverse x means root x. Now let us see some properties of inverse functions. So first is the inverse of a bijective function. Obviously, if a function is a bijective, then only we'll have an inverse. So inverse of a bijective function will be unique and bijective. So if I have f from a to b and it's a bijective, then obviously it'll have an inverse, and that inverse will be unique. Okay, and that inverse will be also bijective. Number 2, if we have a function f from a to b and that is bijective, and g is another function from b to a, and let's say g is inverse of a. Okay, so here we have a function f which is bijective, and g is a function from b to a which is inverse of f. In that case, g composite f will be an identity function in b, and f composite g will be an identity function in a. Okay, like here f is from a to b and g is from b to a. So here this codomain of f and domain of g same. Yes, so we will have f composite g in a to a. That's why, and if that f composite g happens to be an identity element, okay, that will be an identity element if f and g will be inverse of each other. And here if you see, g is from b to a and f is from a to b, so here codomain is a. Okay, and here domain is a. So we will have one function g composite a from b to b, and that will be equal to an identity function in set b. So let us see example for the property 2. Let us see here. So example for property 2, here I have taken two functions f and g. Here a is equal to this and b is equal to this. F is defined as f of x equal to x plus 8, and g is defined as x, g of x is x minus 8. So clearly these two are inverses of each other. Now we observe that f composite g, that would be from a to a, is a well-defined function, and we would see that we would get an identity function. Okay, and G composite F, that would be from set B to B, and again this is a well-defined function, and from the diagram it is clear that G composite F will be an identity function in set of B. So therefore we were able to show this, yes, that if F is from A to B and G is from B to A and they are inverses of each other, then F composite G will be an identity function in set A and G composite F will be an identity function in set B. Now let us go back to properties. Now the third property is, if F is a function from A to B and G is a function from B to C and both are bijectives, okay, then F composite G from A to C is also bijective. So if we have F from A to B, G from B to C, and both are bijectives, then here as codomain for F is B and domain for G is B, so we will have F composite G, we'll have F composite G from A to C, and as F and G are bijective, then F composite G will also be a bijective. Okay, and if this will be a bijective, then this will have an inverse. Okay, once this is a bijective, then this will have an inverse, and inverse of F composite G is nothing but G inverse composite F inverse. So let us try to understand by help of an example. So here see example for property 3. Let us take 3 sets A, B, C. So here your A is this, B is this, C is this, and I'm defining two functions, F that is from A to B and G from B to C. F is defined as this way, that F of 0 will be equal to 2, F of 1 will be equal to 3, F of 2 will be equal to 5, G of 3 will be equal to 4. So here both F and G are 1, 1 and 1, 2, so they are bijective. So clearly they are bijective. Now as F is bijective, so here this is F. As F is bijective, so inverse of F will be this. Okay, because F is taking 0 to 2, 1 to 3, so what F inverse will do is it will take 2 to 0, 3 to 1. So if this is F, then F inverse is this. Then G is a bijective, so inverse of G is here, that is also a bijective. Now here we see that F is from A to B and G is from B to C. So here these two are same, so we can have a function F composite G. Okay, we can have F composite G from set A to C, so A to C, and F composite G will be this. Okay, now next, clearly F composite G is bijective, so this will have an inverse, and inverse is given as this. Okay, because for F composite G, 0 is taken to 5 and 1 is taken to 4, so for inverse of F composite G, 4 will be taken to 1 and 5 will be taken to 0. Now here see these two, we have F inverse from B to A and G inverse from C to B. So here G inverse is from C to B, okay, and F inverse is from B to A. So these two are same. Yes, these two are same. So we will have G inverse composite A inverse. We'll have G inverse composite F inverse from set C to A. C to A. Okay. And this is how this will be. This is how it is defined. Okay. And we observe one thing, that these two are equal. Yes. This inverse of F composite G and this G inverse composite F inverse. So thus we have been able to show how inverse of F composite G is equal to G inverse composite F inverse. So let us go back to properties. Now next property, fourth one. Here it says that if F is a function from A to B and G is a function from B to A, then F composite G is identity in A, G composite this. Already we have seen in this second one. Yes. So if this happens, if two functions are given and this holds, okay, if two functions are given and this holds, then we say that F and G are inverses of each other. Okay, then G and F will be inverses of each other. Next, okay, so this property is important because sometimes it is given that we need to verify whether the given functions are inverses of each other or not. So in that case, we need to show this. Okay. Now, fifth, if F is a function from A to B and it is invertible. So if we have a function F from A to B and it is invertible function, that means F has an inverse. Okay. So in that case, inverse of F will be this. Okay. Inverse of F will be this, and inverse of this will be F. Okay. Basically, it's trying to say that these two are inverses of each other. Okay. And the last, if we have a function F, okay, then we would say that the function is self-inverse if this holds. If this holds for a given function, okay, then we say that the function is self-inverse. Now, method for finding the inverse function, type 1. So sometimes we know that the function is invertible. Okay, that means function is 1 1 and 1 2. So in that case, we only need to find the inverse, and these are the steps that we need to follow while finding the inverse of the invertible function. So in that case, we have to start with this. Fx will be given, so we will put y equal to fx, then we'll solve y equal to fx and we'll make x the subject. Okay, we will solve it such a way that x will be on the left and on the right we'll have some other variable. Okay, that would be in terms of y. And in third step, we will replace x by f inverse y. And in fourth step, we will write x instead of y. So wherever we will have y, those y will be replaced by x. So let us try to find out the inverse of this function. Okay, following those steps. So here is given that f is invertible. That means f is 1, 1 and on 2. So straight we need to find the inverse of this function. So here definition of f is this: f of x equal to square root of 2x minus 3. So here fx is given to us. So in first step we need to put y equal to fx. So y equal to fx. Okay, y equal to fx, that means y equal to this. Now squaring both the side we get this. Then here we have minus 3, it comes this side, so it becomes plus 3 and 2x. Then we get y square plus 3 upon 2 equal to x. That means x equal to y square upon 3, y square plus 3 upon 2. So here we completed the second step also, because we made x as x the subject. Okay, so in next step what we have to do is we have to replace this x by f inverse y. So it's replaced. And in last step we need to replace all y by x, and this is the inverse. Okay, so this is the inverse of the given function. Now type 2. Now sometimes only a function is given to you, so first you need to show that the function is invertible. Okay, and then you need to find the inverse. So once you have shown that function is invertible, then in order to find the inverse you have to follow the same procedure what we have done for the previous example. And in order to show whether the function is invertible or not, we have to see whether the function is 1, 1 and on 2 or not. Okay, so here we have showed that the function f from R to R. So f is a function from set of real numbers to set of real numbers, here defined as f of x equal to 4x minus 7. So we need to show that this is invertible. That means we need to show that f is 1, 1 as well as on 2, and then we have to find the inverse. Okay, so first we'll show that it is 1, 1. Now when a function is 1, 1, a function is said to be 1, 1 if no two elements, like here this function f will be called 1, 1 only if no two elements from this domain have same image. Okay, so we would show it by contradiction. Okay, so what we'll do is we will take two elements here in this R, x1 and x2, and we will say that, let's say their images are same. Okay, so for a moment let us assume that though they are different but their images are same, and we will solve them. And at the end, if we could show that x1 and x2 are same only, then the function will be 1, 1. So here let us take x1 and x2 in this domain such that images of these two are same. So by the definition, f of x1 will be this, f of x2 will be this. Solve it, we get x1 equal to x2. So this implies that f is 1, 1. Now next is on 2. Now in order to show on 2, what we have to show is we have to show that for each element, for every element over here, for this codomain, every element in this codomain has preimage. So if we could show that for every element here we have an element over here, okay, which is related to okay, each other by this definition. Clear? So for that, let us take y equal to fx. Let us take y equal to fx, where y is in R. This R is here in second. This y is in this second R. Okay. So here y equal to fx and y is in R. Note this R is the second one, that is the codomain. So now I have taken y equal to fx. So by definition, fx will be 4x minus 7. Now what we will do is we will solve this and we will show that this x, okay, so we will solve it and we'll show that this x is in this R, okay, it is in the domain. So we have to show that this x is in the domain. So for that, what we'll do is we will make x as the subject. So solve it, we got this. Now as y here, it's a real, so y plus 7 is again a real number divided by 4 is again a real. So this x is a real. So as x is real, that means this x will be here. Yes, this x will be here because here this is set of real numbers. So here that means we have been able to show that this x is in domain. Okay, so it implies that if you take an element in codomain, for that we could find one element in domain which would be of this form. Okay, so clearly y is in real, so this is real, so x is real. Thus we showed that for y belongs to R in codomain, there exists this in the domain such that this is equal to f of y plus 7 upon 4 is equal to, by the definition we get y. Okay, so if you take an element in codomain, so we showed that for that particular element we will have an element in domain of this form. Okay, so that way every element of this R, okay, of this codomain has preimage. Therefore f is onto. Thus f being 1 1 and onto, it is invertible. Now we need to find the inverse. So here we will observe one thing, that we had seen that in order to find the inverse we had to follow those 4 steps. So but while showing onto only 2 steps were already completed. Like this is the first step and this is the second step. So we have already done these 2 steps. So now we only need to do the third and fourth step. So in this only we need to replace this x by y, f inverse y. So here we have replaced this x by f inverse y, and in the last step we will replace all y by x. So that way we get the inverse of function f. Okay, so here function was defined as this and inverse of this function is this. Now let f of x is this and g of x be this. So we have got 2 functions f and g, and this is how f is defined and definition of g is this. So here question is use composition to verify that f and g are inverses of each other. So in order to show that they are inverses of each other, we need to show that f composite g of x is equal to z composite f of x equal to x. So in order to show that, we would find this separately and we will find this separately. And if we see that f composite g of x also comes x, and g composite f of x also comes x, so in that case f will be inverse of g, or we can say the inverses of each other. So here f composite g of x, then by definition of composite function g of f of x. So here if you see definition of g, so if you have x, then here output is this 3 times x, 3 times whatever you have over here, upon this whatever you have over here plus 2. So here by the definition g of fx will be 3 times whatever here we have, so that is fx upon fx plus 2. Then you put the, by the definition of f will have this, yes, solve it, will get x, and g composite f of x, this will be f of gx. Now here we see the definition of f. So if you have x over here, then output is 2 times x upon 3 minus x. So by the definition of f, we'll have f of gx will be equal to 2 times this whatever you have inside, gx upon 3 minus gx, and then we'll put the value of gx, okay, by definition of this. So and solve it, again we'll get x. So thus we were able to show that f composite g of x is equal to f composite g composite f of x equal to x, and therefore f and g are inverses of each other.